So we have object-oriented programming, right? Like C++, C#, Python, Java. And we can do a lot of really cool things in it, like polymorphism, where we have classes that are related to each other and derived. So how does that work on the assembly level? Let's take a look. We're going to start with a really basic example in C. We can do a really short course primer on assembly and how calling works. And then we'll step into object-oriented programming and see how those object references are passed, how they look in memory, and how it all ties together to execute on the CPU. Let's look at a simple C program. We're going to have our main function here. And let's write a second function called hello. We're going to print hello world to the terminal. Let's write in our call here. It's going to run the program. We're going to call hello. It's going to jump here and print this out. If we look at the simplified assembly here, the hello world string is read-only. It's a string literal. So that's put into the data segment of memory. And then what we can see here are two functions. So what happens during compilation is we're going to split up main. He's going to get his own function in assembly, and hello is going to get his own function in assembly. And when we start the program, hello is going to be called here. So the CPU is going to jump to hello, and then it's going to do some stuff on the stack for local variables and for the calling conventions. But this is all just stuff that we don't really need to pay attention to right now. It's going to save the previous function's base pointer, and then it's going to set up its own stack frame. And then what's going to happen is it's going to call the kernel call of write. And this is ultimately what's executed when we call something like printf and we're printing to the terminal or to the standard out buffer. So we don't need to pay attention to that either. But the key point here is to lay the foundation for these examples so that as we move forward to object-oriented programming, we have a basic understanding of what's happening with the assembly. So the program starts, we call hello, and then we're going to tell it that we want to output this string here, which we're just going to call message. And you can see that we're loading the effective address of message into the memory, and then we're going to call the kernel call to execute that. And if we look at the disassembly here, the function hello has really just been mapped to these memory addresses. And when we're going to call it, instead of call hello, the actual instruction being executed by the CPU is the actual memory address. So 4000 C1 is the start of the hello function. And we're just going to jump there, and then we're going to execute, and then we're going to return to the next line where we exit the program. And to make it crystal clear of what's happening with the string, the compiler is going to look at the string literal and put it in memory. The linker is going to make sure that it's at the right address and all that. And in this case, the string literal has made its way to 4010E5. And again, to make it even more clear, I wrote them out individually. Each one of these characters is 1 byte. So you could see at E5 we have H, E6E, E7L, so on and so forth. And it's going to populate that, call the kernel, and it's going to output it. So this is a very basic example to kind of get us going. Now, what if we wanted to pass a argument to the hello function? How does that work? So let's go over that, and then we'll get to the object-oriented stuff. So let's say we have our main function again, and now let's say that we're going to have a print function that takes in a string. So we're going to just simply use printf again. Of course, we're not really showing printf with the C library, but we're just showing the actual instructions that are going to be executed on the assembly side. So let's just call the print function and let's send in a string like ahoy there. So how does this work, right? How do we pass an argument to a function? Because we need to know this when we're doing object-oriented stuff, when we're passing references. And in this case, if we look at the assembly, the string, right, has been allocated again here in memory. The way it looks to us right now is we're going to call a function and then we're going to tell it, hey, you're going to take these arguments. But in reality, what happens is we populate the arguments first, and then we invoke the function call. The way that we pass this as an argument, we're going to move the memory address of S, where the string is in memory. And if we look at the disassembly over here, we can see the address that I got, 4010E3, is a start. That's where A is, and then it goes down like I had in the last one. So ahoy there is at E3. So S is really going to be E3, and if we look up here, that's exactly what it is. So we're going to move the address of this string to the first arguments register, and this is just a calling convention that everybody has sort of agreed to use on x64. The first argument goes in RDI, second argument goes in RSI, third in RDX and RCX. There are 6 registers that are used. After that, if you have more than 6 arguments, then they just go on the stack. So in this case, RDI is the first argument. So we're going to put the memory address into RDI over here, and then we're going to call print, and print of course has its memory address here, which goes down here, and it executes the same function. That's how we send arguments. We populate these registers and then we call the function, and then they're going to catch it. It's kind of like we're throwing it to them. The print function is going to use it the way it needs to do the system call write. Now let's move on to the simplest form of what we'd call an object. We're not quite at object-oriented programming yet, but the first step to that, in my opinion, is a struct in C, where we have a group of data that's held together in a contiguous block of memory. memory. So in this case, let's say we're dealing with animals. Let's say that we give the animal a name, we give the animal an age, his weight, and his favorite food, which is another string. If we look at the memory layout for a struct, let's say an animal at address 10E8, since we know that it's a pointer to a string location, that's just going to be an 8-byte address since we're on 64-bit system. The integers themselves are going to be 4-byte values or 32-bit values, so the actual integer values are going to be the raw data, and then we're going to have the pointer for the favorite food. So altogether, an instance of an animal struct is going to be 24 bytes. Let's say we give him a name Bob, and his favorite food is beef, then all we're going to have for the name is a pointer to this memory address, and this one's going to be a pointer to this memory address, right? So name is going to point to where Bob is located, wherever the linker put it in memory, and the favorite food is also going to be a pointer to another string that's somewhere off in memory. So in this case, we just make this up. 112C is where beef is located with the null terminator at the end, and we just point to it. So this is an instance of the animal struct. You could say it's an object, right? It's a group of data together. And we have literal values and we have pointer values, or we could say references, right? We have references to these strings, which is very much how it works in object-oriented programming. So let's continue with this example, and then we'll get to object-oriented programming in the next example after this. So if we have our struct here, and let's say we instantiate one of them, and again, we give it the Bob name, beef is his favorite food, he's 5 years old, let's say, and 7 kilos or pounds or whatever you prefer. And we have our main function here. And let's say that we want to interact with this data. Let's say that we have a function called animal print food. And what we're going to do is we're going to pass in an animal reference. And the function is just going to print out the favorite food of that animal that we passed in. So very similar to object-oriented programming here. We could imagine that this is like a method, but in C, we don't have methods. They're all just functions, so we have to pass it in manually, right? And the way that objects references are passed, whether in C with structs or in object-oriented programming, is you send the reference to the start of the data. So in this case, we have our name. We could say at offset 0. So as soon as we have the A variable, the first piece of data is going to be that 8-byte pointer that we had. So what we're going to do is we're going to pass the address, which is that first position. And then when print food gets it, right now, remember, we're looking for favorite food. And we can see that in the list, there's 8 bytes for the name, the pointer, there's 4 bytes for the age, and there's 4 bytes for the weight. So 8 plus 4 is 12, plus 4 is 16. So we really want to go 16 bytes into this memory address. And this is all kept track by the compiler. So in this case, we know favorite food starts at offset 16. So we're going to pass the starting location of this object into RDI. Print food receives it. And you can see he's going to offset it by 16, right? Looking for that favorite food, looking for that pointer. And you can see it down here in the disassembly. It's going to be different to the example I showed before because I made up the example before where I showed the layout. But this is the actual memory where it was stored. So at E8, we have the pointer to the name, which has been put at 1128, right? By the linker. So we have the string pointer to this location, 8 bytes. We have the raw data for the integer, 4 bytes, right? 32 bits. We have another one, 32 bits. So 8 bytes, 4 bytes, 4 bytes is 16 bytes. And then at the end here, we have this string pointer, 8 bytes again, going to beef. So if we wanted to access this, we have to skip 8, skip 4, and then finally we're at 16. And once we're at 16, we're going to be right at the start of this data here. So we're going to move that in, and then we're going to do a system call, and it's the same thing as before. And you can see, by the way that it's declared is animal A, right, that we have in our code. In assembly, turns into just another sort of definition here in assembly, and we have define quad, which is a quad word, that's 64 bits. One word is 16 bits, so 4 of those is 64. And you can see that we're sending the address of animal name where we define Bob. So the way that the compiler writes this and the assembler looks at it with the linker is it's going to say, well, we have a value, we have a string here, we have a series of bytes that we're going to put in memory, and we're going to keep a reference to it, animal name. Just for the assembly. When I say reference, I mean just for the assembly process. So it's going to put Bob in memory, and he's going to say, hey, wherever he is, we need to keep track of it because this guy, where we declare A, he's going to want it. So A gets the address of where Bob was by way of animal name as a reference. And the same thing for animal food. We declare animal food here as beef. So we define beef. It goes into memory. It keeps a reference for us, again, only during compile, right? Only during assembly and linking. None of this is done during runtime, at least in this example. And then we have the literal values here of the integers. And then, of course, we have the defined quad for the 8-byte pointer, right? 64 bits, 8 bytes, same thing. So this is the start of the object-oriented. And you can see that the complexity has gone up a bit, where we have to use offsets here to access these data members. Because if we just sent in RDI, right, this value here, without offsetting, then what we would actually print is Bob, because it would just be at E8. And the kernel call write would look at this address and just print Bob. So this is the struct, right? This is how any collection of data, and that's what an object is. It's just a collection of data in a contiguous block of memory. So let's move on now to actual object-oriented programming. So using the same example as before, let's turn it now into a class. Same thing. We have a name, age, weight, we have the favorite food, and let's give it a method called speak. And he's going to say me animal, you human. Right? Because he's a regular animal. We don't really know what he'd say. He could be any kind of animal, a bird, dog, whatever. So he just says me animal, you human. Now we're going to instantiate an instance of this class, right? Now we're in object-oriented mode, and it's going to be put on the data segment, right? It's a global variable. It's outside of the scope of anything. We have our main function here. So here's our assembly for it. And you can see that methods are no different to functions in assembly. The compiler itself is going to convert this method in animal just to a function. It's not inside of anything. It's not protected by anything. There's no access modifiers. All of that is strictly compiler stuff. When it comes to the actual instructions of the CPU, he doesn't care or even know whether you had this as public or private or anything like that. And if we look at this assembly real quick, we can see that A has the same exact memory profile as the last one. The last was a struct, but this is an object. Same exact thing. We have a pointer to the name, which is Bob down here. We have an integer, another pointer to beef. And then we also have a string literal here, right? Me animal, you human. And that's going to get its own memory address that we can then reference later on. So let's move on. What we're going to do is we're going to call A and the speak method. We know that before with the struct, we had to actually pass in A in assembly into RDI. So the question is, how does it do it behind the scenes? We have our object here, we have a method, but what happens behind the scenes? Well, funny enough, the compiler is going to do the same exact thing that we did. Whereas we did it explicitly, the compiler does it implicitly. We can now call a.speak, but what the compiler is going to do is unwrap this into the same exact line of code that we had. We're going to move a, right, the start of that object instance, into RDI and then call animal speak. So it's literally the same exact thing that we did, except the compiler now does it for us. So in this case, this first level of object-oriented programming is really just a benefit to us by organization, keeping these methods tucked away so they're not like in the way of what we're doing. But when it comes down to the actual assembly and the CPU and the code that's executed by the CPU, then it's the same exact thing. The compiler just does it for us. Nothing changed at all, except that we skipped having to pass a reference to A on its own. The compiler does it for us. So moving on now, let's add a feature of object-oriented programming because it gets more complex, right? Let's look at polymorphism. We can have something that derives from animal with the same method name overridden, and the compiler has to know what it is that we're doing. So let's see how that is worked out. So here's our class again. We have animal, and now we have the same function, me animal, you human, but it's now virtual. We're going to be able to override this, and we can see how that's done with assembly. Let's create a derived class, dog, and inherit from animal. And then let's override the speak function. And now he's able to say woof woof instead of me animal, you human. So we get rid of our placeholder. Now he's a real dog. Let's declare the variable. We have to set the data here. And then what we're going to do in main is we're going to call speak. Okay, so same thing that we did before. Let's look at the assembly. We can see here that speak from animal gets its own function declared, and speak from dog gets its own function declared. This is pretty much what you'd expect, right? They're technically different methods, even though they're connected in a way, but they're different methods, different functions in assembly. Now the question is, of course, when we call speak on the dog, how does it know which one to call? So as soon as we add a virtual method, something special happens. If you remember the object before, we had name at offset 0, right? Just the base address. Then we had age 8 bytes after because name was 8 bytes. Age is 4 bytes. It's an integer, so now we're at plus 12. That's where weight is. And then remember, we wanted to get favorite food, which was at 16. However, now with virtual methods, there is a secret first entry that's added. It's a pointer. Another 8 bytes is added to our object. So whereas before, the whole thing was 24 bytes, remember? Now it's going to be 32 bytes. 8 bytes has been added by the compiler. It's a pointer, but not to a string. In memory, what's going to happen is it's going to build this virtual table. And the virtual table is just a bunch of pointers. And we're going to look at this in memory in just a second, but I think going over it first will be helpful. So the virtual table called a Vtable is going to list out all of the virtual functions so that we can keep track of which derived class overrides which function. So all we need to know right now is that there's a pointer here, a secret pointer, and there's a virtual table that will be built by the compiler. So if we look at the class layout for the vtables of animal versus dog, let's say we had a bunch of virtual functions here for animal. We choose to only override one of them, speak. So animal has a virtual speak, eat, and sleep, but dog only overrides speak. That means eat and sleep. When you call it on dog, it's just going to call the definition, the implementation that's already on animal. So the vtables for both of these, if we look at them, the first entry doesn't matter. It's just information about the type. For our purposes, it doesn't really matter. But you can see the order after, it's just pointers to the right functions, right? So animal, of course, being that base class, is always going to take its own definitions. Animal speak, animal eat, animal sleep. But the dog class, the compiler is going to say, hey, did he override speak? Yes, he did. So he's going to replace this pointer, right? Override it. That's where its name is from. It's going to override this memory address to go to dog speak instead of animal speak. And then the compiler is going to say, okay, did he override eat? No, he didn't. So he's just going to call animal eat. And he's going to leave this one unchanged too because we didn't override sleep. So sleep is just going to call animal sleep. And this order is adhered to all the time. There's no other way for a machine, right, to know where to go. Well, there is actually in Python, which we'll get to that. And that one is like a different animal entirely, no pun intended. But in this case, all we're doing is using offsets. And so the compiler keeps track, hey, offset 8 of the vtable for anything derived from animal is going to be speak. If it's overridden, it's going to replace it with its own memory address. If it isn't, then it just goes to animal speak. So this is how the vtable looks in memory. So we had the animal class, we have the dog class, we have the two functions, methods, it's overridden, but they exist separately in memory. And now what we can see at the bottom here are vtables that are defined now, declared by the compiler. So what it's going to do is the dog class is going to get just a list of pointers at the same offsets. So our animal and our dog are going to get the virtual tables built for it. And if we look at it in memory, the animal vtable over here, then we can see that it's two different pointers. One of them goes to A8, which up here is just the animal name that I put just to define the class. It knows the name of its own class. This is like the real-time type information. But the second one is where the real virtual pointer table starts. And E7 is a location for the speak method for animal itself. So E7 is all the way up here, and we can see animal speak is at E7, and it performs it there. And then the dog version of speak, the overridden one for woof woof, is here, and that's at, it seems like C8. So if we look at the dog's vtable, then we see C8 is that first virtual method. So what's going to happen is the compiler, when it needs to, is going to basically just get a reference to the object, which in this case is D, right? We declared dog D for dog. And you see the first entry is that secret link, define quad, right? 8-byte pointer, 64-bit memory address, vtable for dog. So it's going to get a link to vtable for dog. When we want to call speak, we know the instruction is we go to the dog, we follow his vtable, and then we go to the second address listed, and that's speak. And the compiler, again, keeps track of these offsets. Just like how it knew that favorite food was at 16 bytes offset, it's going to know that anytime we call speak for anything derived from the animal class, it's going to be in that second entry of the vtable. So the vtable has speak. It needs to be in this exact order for all classes derived by animal. Now, in this case, it's kind of a funny thing here. When we look at the actual code, the compiler, which optimizes the heck out of our programs when we ask it to, and usually that's by default, it's going to take any shortcuts that it can. So this assembly, a lot of it may be missing in a real world environment because of the optimizations. Like, we don't really use a bunch of this data that's here, but I have it, of course, for illustration. And we can see one of the optimizations made here is when we're going to call dog speak, you would expect it to do what I explained, where it looks at D here, goes to the vtable, looks at the second offset, and gets that link, dog speak, which is up here, and then it calls speak. And it takes many instructions to do that, but that's the price we pay for dynamic and expressive programming. But it doesn't do that at all. Instead, the compiler just calls dog speak directly, right? So you might be saying, like, what are you talking about, right? What am I talking about with all the vtable jumping and stuff? The key fact here is that the compiler, whose prime directive is to write clean code, optimized code that works, it knows, right, that this is a global variable. It's dog. He'll never be an animal. He's always going to be a dog. So the compiler skips any of the lookups that it needs to do, vtable, down here, get the offset, and then link to dog speak. And it could just put dog speak directly. In this case, call, just like the other examples that we had, it's just going to call C8 directly and go directly to dog speak, where it's right here. So what we need to do to see the vtable in action is confuse the compiler. Make it not so sure that it's a dog. And we can do that very, very easily. let's write a function called pet animal. So we, the human, are going to pet an animal, and he's going to love it. So he's going to make noise, right? So we're going to pass in an animal, which could be an animal, could be dog, right? Because he inherits from animal. Which one is it? Who knows? So how does the compiler keep track of this? We'll see the vtable in action now. And if we refine our main function here, then we're going to pet the animal, right, of dog. So we have the same dog that we had before, and we're going to pass it now to pet animal, just like we saw before, where we pass the memory address of D, right? And D, of course, has all of our data like before. It has a vtable now. D is at right here in 38. So 38 is the memory address that is passed to RDI. And then we're going to call pet animal. And the pet animal function has been mapped here in assembly. Pet animal is going to take the value of RDI, which is the address for D, okay, at 38 here. But there's brackets around it. So it's going to go to that location, 1138, and then it's going to put the address found there into RAX. Then it's going to go to the address found at RAX, so 1198. It's going to look at 1138 and copy this value. Then it's going to go to 1198, which is now in RAX, and add 8 to it, which skips the real-time type information, the first entry, and it's actually going to grab the address of the second entry in the vtable, which is the location of dog speak. So that's C8. So if we go all the way up to C8, we can see C8 is where dog speak is. So the vtable is being used here, right? It passes the memory location of dog. Then it looks at this value with the brackets, goes there, skips 8, calls this value, and goes to dog speak. And we can see the animal vtable has a second entry as well. But of course, this is going to go to the animals version of the definition, E7, up here, animal speak. So the key idea here is that no matter what we pass in there, if it's derived from animal, following the same instructions will lead to 2 different functions, depending on whatever pointer is in here. So this is how the vtable is used. And this is how polymorphism is accomplished. So it's worth noting here that in C++, the vtable is only added when we have a virtual function. Otherwise, we saw, just like in C, there's nothing but the members in there, the data members. So when we add a virtual function, we get the vtable pointer. And we can see, again, the vtable layout. We have the type information, and then we have any of the virtual functions. Even if they're not overridden, they're in there. In something like C#, we always have some pointers at the start of our objects. And this is why the higher level you go is sort of like the more space it takes up, and sometimes the longer it takes to execute. So in C#, it would be a very similar example. However, by default, C#, just like in C and C++, it's going to call those functions directly if it knows what type it is. It's not going to make a virtual table or anything like that unless it has virtual functions. It does have a method table with some information about the class, but the actual virtual part, overriding part, using the vtable to navigate and using indirection and dereferencing is only going to be used when we have actual virtual method in C#. However, in something like Java, if we look at C# over here and Java over here, then C# has, like we just said, those method tables, right? And then the data information for that object instance. And then, of course, the method table is going to have any of the virtual functions. But only virtual functions show up in the list. Anything non-virtual is going to be static dispatch by default. And that's when it just calls it directly. Java, on the other hand, everything by default is actually virtual. So anytime you have a method in Java, it's going to look it up in the vtable, unless you use something like private or static, where it won't be used as a virtual function. So by default, C# has static dispatch, and by default, Java has dynamic dispatch. So it's kind of like reversed. And of course, these objects run on virtual machines, the .NET framework, just-in-time compiler, but code has to reach the CPU, of course, in all cases. So we're talking about the actual code that's executed on the CPU. And there are all sorts of optimizations and shortcuts that are made. So what I'm saying might not be exactly correct in every scenario, but generally speaking, C# uses static dispatch when it can, but Java only uses dynamic dispatch unless explicitly told not to with something like private or static. And if you use final, then it will just ignore any kind of, I guess, overriding or not let you do it in the first place. Now let's look at Python. So Python takes everything a step further. And instead of using a vtable, instead of using offsets, the way that we do in C, C++, C#, Java, what Python does is it actually adds every single member to a dictionary, to a hash table. So let's look at our class again, right, in the version of Python. And let's say that we have animal and we have speak method, eat, and sleep. And then we have the dog class that defines speak as well. And this is an override, right? This is what we would call an override. So let's give the dog some values here. His name is Rex. He's 5, weight is 20. I guess I forgot to give him a favorite food. All of these variable names are going to go into a dictionary of Python objects, but basically strings. And anytime you want to access any of these fields, it's going to hash the name and look it up in a dictionary. And it's not just one dictionary. When you have an object, then the object itself is going to have at offset 0 a pointer to its class object, which we'll put down here, and it's going to have its own dictionary for the instance itself. So when we have this instance of dog and we're setting those variables for this one instance, right? This is the only instance where name is Rex. Then what it's going to have is it's going to build a dictionary where when we hash name, then it's going to be a pointer to where Rex is. We don't have offsets like in the other languages. Anytime we want to access name, it's going to hash it, look it up in the dictionary, and then fetch it from memory. Now there is caching and stuff like that will make it much faster on subsequent calls, but this is how it works. So every instance of an object in Python has its own dictionary. And this works for methods too. Let's say that you add a dynamic method at runtime that doesn't belong to the class. Then that method, the way that that's able to be possible is we could just look up the method name in the dictionary. Now, what if you can't find it in the dictionary, right? What if it's nothing unique to that instance? Well, in that case, it would be in the class dictionary, and it's going to have a pointer to its base class. So in this case, if this is dog, then the first offset is going to be a pointer to animal. And this is the only amount of offsetting that we're going to be doing here. It doesn't use the offsetting like I mentioned in the Vtables themselves, because there are no Vtables, it's dictionaries. So it's going to have a pointer to its base class. It's going to have some class information, which is fine. And it's going to have a method resolution order, which keeps track of what dictionaries you check in what order, because there's not only two. So let's use an example here. Let's say that animal has eat, right? But dog doesn't define eat as an overridden method. So what's going to happen is when we call dog.eat, right, d.eat, it's going to check in its own dictionary and see if we have the definition for eat here, and we don't. So he's going to follow the pointer to his class object, go down here, and then he's going to check this guy's dictionary and say, hey, do you have an eat? And if it's in dog, then he'll follow it. And if it's not in dog, then he's going to look at the method resolution order, which just keeps track of all the classes that are in that sequence, and go up to animal and check animal's dictionary, which will just look very similar to this, but it'll just be animal with the same thing, and check it for eat. So anytime you access anything in Python, it's going to consult the dictionary. It's going to look at the string that you have. It's going to hash it. It's going to probably use some kind of modulo function to put it into the table, index it in, get the value. If it can't find the value, it moves to the next dictionary, does the same thing, gets the hash value. Doesn't need to rehash, but remodulos it into that table. If it doesn't find it, goes up to another class, and up and up and up and up. So Python is just an entirely different beast. It's super, super dynamic. And that's because we pay for it in all of these steps. I mean, to have a dictionary lookup every time you're accessing a variable, not including caching, is incredibly expensive, but it gives us a level of freedom that's pretty unmatched. And one thing that we didn't really talk about too much is the actual data members themselves. Let's say that we have the dog again that derives from animal. But now let's say that we also have a beagle that derives from dog. And each of these have their own data members, right? So animal has its data members, dog, let's say, adds a bark volume, and beagle, let's say, just adds a colors where we have flags for different colors or something like that. So how would this look in data? If we look in the memory, then we'll see that they're just lined up in the order in which they appear. So we have the animal data here, then the dog data, and then we have the colors for the beagle. So the offsets are just always going to make sense. The animal will always come first in this case, then the dog, then the beagle. And anything that inherits or derives from beagle will just continue to be added to the list. The compiler will make sure it keeps the same order. So anytime we have a beagle, the compiler will know that offset 8, for example, is a name, offset 14 is a weight. It's just going to keep track when it builds them together. The data members, it's still going to be one contiguous block, and they're just going to be in order. And this is true, of course, because we know anything that ever derives from beagle is also a beagle, is also a dog, is also an animal. Just like a beagle is always a dog, always an animal. So it's not like this order will ever change. So it's just a matter of the compiler, again, keeping track of the layout. And anytime we're going to try and access something, like if we had a beagle, let's say B, if we wanted b.weight, then it would just say, okay, beagle inherits from these classes, so weight is at offset 14. And that's pretty much it for accessing the members. So this is just an overview of how object-oriented programming works on the machine level. It's, of course, at the end of the day, just instructions on the CPU, but the data is organized in a way where we can have patterns and repeatability. And the compiler itself is the one that really does a lot of that heavy lifting, keeping track of offsets, of tables, of variables, so that we can feed it into the CPU. So thanks for watching, and I really hope this helps. Let me know if there's anything that I can go into more, anything that I missed, or anything that I was mistaken on. But in the next video, I think what I'll do is go into a bit more assembly before moving on. So maybe the next video will be writing some simple functions in assembly and go on from there. So thanks a lot for watching, and I'll see you soon.